All right, guys, in this lesson we're going to be looking at power and type 2 error. So our objective here is just to interpret the power of a test and describe what factors affect the power of a test, and we're also going to describe the relationship among the probability of a type 1 error and the probability of a type 2 error, or the difference between significance versus power, basically. So what we need to do is let's first kind of review a little bit, because we really went over confidence intervals in Chapter 8, whereas we're going over significance tests in Chapter 9. And there's a lot of similarities. And one thing that I didn't have you do in Chapter 8 is use the 4-step process to solve for confidence intervals. However, kind of as I've looked more at this, AP readers are really going to want you to use that process in order to solve for confidence intervals, or in order to show your work in solving for confidence intervals. So it's just kind of good practice to understand what this is, basically. So first thing we need to note is that we have the state portion of our problem. We have the state, we have the plan, we have the do, and we have the conclude. Okay? So all 4 of those make up the 4-step process, basically. So the state portion of this problem is really going to be involved with, in both instances, the confidence interval and significance test. You first want to identify the population and parameter in context of the problem, basically just stating what specifically we're looking at in the problem. When we're looking at confidence intervals, we don't have to come up with a hypothesis, but when we're looking at significance tests, we want to make sure that we state the null and alternate hypotheses for that particular problem in the state portion when we're solving that 4-step process. The plan portion is going to involve the conditions, so checking to make sure that all of these conditions are met, that the sample is random, and most of the time it's going to say in the problem that the sample is actually random, whether or not it's independent, so whether or not the sample is 10%, is less than 10% of the entire population as a whole. So making sure that it's independent and making sure that it's a normal distribution. And again, that can come in multiple ways. The problem can say that it's a normal distribution. You can use the large counts condition to make sure that the successes and failures are both greater than or equal to 10. And you can also check the central limit theorem as well to make sure that there are 30 or more people in the sample as well for that. So all of those would suffice for the normal distribution. From there, we want to focus on the do portion. So first, for confidence intervals, we would really need to focus on the critical value, or solving for z or t, and you can do that using inverse norm or inverse t for t. For significance tests, we want to look at alpha, or our significance level, and a lot of times that's going to be given in the problem. We're really not going to solve for that on our own. For confidence intervals, we want to look at our test statistic, which is really just the actual confidence interval itself. So that's really all we're solving for in the do portion. And then we also want to interpret that confidence interval as well. So we are, whatever our confidence level is, we are that much confident that the true parameter, whatever we discussed up here, lies in the range of whatever our confidence interval actually is. When we're looking at significance tests, though, we want to actually solve for z right here, but we also want to solve for p as well. So we also want to find our p value as well in the do portion of this particular 4-step process. So that's also something to note, that we're not just looking at the test statistic, which is represented by z, but we're also going to be finding the p value as well. When we're looking at and really you wouldn't want to include, this is more part of the conclusion, or the interpretation of a significance test is more part of the conclusion than anything. So really the conclusion is going to come down to, in many samples of size C for confidence intervals, whatever our confidence level will contain the parameter that we're discussing. That's essentially going to be what the conclusion actually comes to. When we're looking at the conclusion for a significance test, we're going to be interpreting whatever we found in the do portion. So since our p-value relates to alpha, we decide whether to reject the null hypothesis or to fail to reject the null hypothesis based on whatever our p-value is and how that relates to our significance level. And then we also want to state, as alpha changes, the probability of making a type 1 error changes. basically. So, and we don't necessarily have to include that in our conclusion, but that's kind of what we're going to be looking at here. So again, just kind of wrapping up the difference between these two things, confidence intervals and significance tests. The difference is really in the result. A significance test tells you what you should think of the null hypothesis in terms of the statistic that you found, whereas a confidence interval tells you the range for a parameter based on the statistic that you found. So the test tells you if the evidence makes the alternate convincing or the proportion has changed, but the confidence interval tells you a range where the parameter might be. Or in other words, we're 95% or 90% confident that it actually changed to this, basically. So let's kind of rewind and let's look at what we really should be looking at, which is power and type errors, basically. So just kind of a rehash. A type 1 error, and I'm going to draw a little box here just to kind of make it all make sense. So our type 1 error is when we reject a null hypothesis in favor of an alternate hypothesis, but the null is really true. So again, let's say that our null hypothesis is true on this portion, on this column, and our alternate hypothesis is true on this column. However, let's say that we reject our null hypothesis for that row and then fail to reject our null hypothesis on this row, right there. Our type 1 error is when we reject the null hypothesis, but the null hypothesis is actually true. Our type 2 error is when we fail to reject the null hypothesis against evidence of an alternate, but the null was actually false. So this is when our alternate hypothesis is actually true, but we failed to reject the null hypothesis. So we accepted essentially whatever this was right there. The chance that you will make a type 1 error is the significance level of the test, whereas the chance that you will make a type 2 error is known as the power of a test. So really, when we're looking at this idea of power here, power is the probability that a test will reject the null at a given significance level when the alternate is true. So really, power is what we want. We want whatever our power level is, or the number that represents power, we want that to go up, because that's going to reject the null hypothesis when the alternate is actually true, basically. So let's look at that example, at this example real fast. The potato chip producer wonders whether the significance test of our null hypothesis, where our proportion is 8%, versus an alternate hypothesis where the proportion is greater than 8%, based on a random sample of 500 potatoes, has enough power to detect a shipment with, say, 11% blemished potatoes. In this case, a particular type 2 error is to fail to reject our proportion of 8% when our proportion is actually 11%. Our figure on the next page is going to show two sampling distributions of p hat, where one where our proportion is 8% and the other where our proportion is 11%. So let's say, just for this problem, let's say that our alternate hypothesis is actually true, where our proportion is 11%, so that is greater than 8%, but we want to make sure that we reject that proportion of 8%. So this is kind of a visual representation of that. So the bottom graph, the power of the test, or the shaded area, is the probability that it correctly rejects our probability of 8%, when the truth is that our probability is 11%, or our proportion is 11%, excuse me. In this case, our power is represented as 0.7626. The probability of making a type 2 error is what's represented in this white area, 1 minus whatever the power was, essentially. So what we really need to know is, again, power is a good thing, basically. So this is the probability that we are going to reject our null hypothesis, essentially. But we have about a 76% chance of that happening. However, we also have a 23% chance of making a type 2 error, where we essentially, our alternate hypothesis is true, but we failed to reject that. We also need to just kind of review on the fact that the probability of our type 1 error is represented by alpha, right here. So that's represented by our significance level. This is, again, the probability that we reject our null hypothesis when our null hypothesis was actually true. So just kind of remember these visual representations of what these actually represent, basically. So again, the power of a test against any alternative is 1 minus the probability of a type 2 error for that alternative, which is essentially what we just kind of went over in this area right here. So basically, what affects power? What makes power go up, down, anything of that sort? Because again, we want to increase power as much as we can. So there are really 3 ways to increase power. The first way is that we can increase the sample size, which decreases variability with reduced spread. So again, understanding that if we increase our sample size, that's going to increase our power while also decreasing the probability that we will make a type 1 and a type 2 error. Okay, so really the safest way to do this is to just always increase the sample size, but sometimes that's fairly hard to do, okay? Especially when, if you were completing a study in real life, you would want to find as few people as possible to perform the study on and still get semi-accurate results, basically, that still represent the entire population as a whole. Because it's hard to get people to perform studies on. So really, that's honestly the safest way to do it as far as increasing power is we would want to increase our sample size. We can also mess with our significance level as well. So we can increase or decrease our significance level in order to affect power, basically. So if we increase alpha, or our significance level, that's going to increase power. However, that is also going to increase the probability that you make a type 1 error as well. Because if you remember from the visualization over here, if we increase this number right here, that's going to make more area under the curve, which means that that also directly correlates with the probability that we make a type 1 error. So we really want to and before I get onto that, it's also going to decrease the probability that we get a type 2 error as well. Okay. So really what we need to do is we need to discern whether or not it's more harmful to make a type 1 error or more harmful to make a type 2 error before we decide to adjust our significance level in any way. On the flip side of that, if we decrease alpha, that's also going to decrease power, and it's going to decrease the probability that we make a type 1 error, but it's going to increase the probability that we make a type 2 error. Okay, so really kind of understanding how significance level affects the probability that you make a type 1 or a type 2 error is really trying to understand which one is more harmful. Is it more harmful to make a type 1 error or more harmful to make a type 2 error? And really at that point, that's when you discern, okay, I should either raise my significance level or lower my significance level for this particular test. We can also increase the difference between the null and alternate parameter values that the test is trying to detect. So this will move the peaks of the distribution further apart, essentially. So that's another way that we can increase power in this case. So let's take a look at this example real fast. If we refer to the perfect potatoes example that we just looked at, which is more serious for the potato chip producer in this setting, a type 1 error or a type 2 error? And based on your answer, would you choose a significance level of alpha at 0.01, 0.05, or 0.10? So really, for this part, from the chip producer standpoint, a type 2 error would be worse in this case. So you would use blemished potatoes to make your chips, which is not good. So a larger alpha would reduce the risk of a type 2 error. So we should use alpha at 0.10. And again, just remembering this little visualization right here, where if you increase alpha, that's going to decrease the probability of our type 2 error, because in that case, we would not want to use blemished potatoes to make our potato chips. So I want to use the highest alpha that I can possibly use if increasing my sample size is not going to do the trick, basically. Number 2 for this example says, tell if each of the following would increase or decrease the power of the test, and we want to justify our answers. So part A says that we could change the significance level to 0.10. B says to take a random sample of 250 potatoes instead of 500 potatoes, and C insists on being able to detect that our proportion is 0.10 instead of 0.11. So A, increasing the alpha level makes rejecting the null more likely. So that's, again, always going to, when we increase alpha, that's always going to increase the probability that we make a type 1 error, or the probability that we reject the null when we really shouldn't reject the null. If we decrease that, a smaller sample means more variability and thus more spread. So decreasing the sample size of the potatoes is also going to decrease the power, as well as increase the type 1 and type 2 errors. So that's really kind of not a good scenario at all. We probably want to make sure that we get as high of a sample as we possibly can in this case. And if we want to decrease this part right here, that would mean to increase the power would make the difference between the null and the alternate greater in this case. So that's essentially how we would want to answer each one of those parts for part 2 of that.